Fourth, chapter 3, flow over immersed body. This is actually the continuation of before internal flow, and this is external flow. This basically cover boundary layer, drag, and lift. If you talk about these things, it is really related to aerodynamics or maybe airfoil design. To practice, we're gonna do two exercises. The first one is related to car aerodynamics, and the second one is related to airplane drag coefficient. So let's start from the first one, number 42. As you can see here, we zoom out first. There are two conditions. The first one, the windows and roof closed. We got coefficient of drag equals to 0.35, while when windows open and roof open, we got drag coefficient equals to 0.45. Well, to compare, we have the same amount of power. Let's say that powers can move the first condition to the speed of 95 miles per hour. While with the same power, how fast the second condition car will go. Okay, let's do this. Well, the first one, we're gonna find out the relation of power to force and velocity. And we found out this is the drag coefficients, and then we find out which are constant, and we put all this formula into an equation, and we cancel out all the corresponding equation, the corresponding variable, and finally we got the ratio for v2 and v1. Putting the numbers, we're gonna get the velocity for second condition equals to 60 mile per hour. Okay, that's the first one. Let's move to the second one. We're gonna analyze a design of airfoil. I mean airplane. So this is the illustration of the airplane. What we are going to do is we're going to determine the ratio of drag from the wire bracing, like here, to the wings. We got all the information, and let's point out that we got the drag coefficient for wings is 0.02, but there are no information about the wiring drag coefficient. So to answer this, what we are going to do, we are need to find the drag coefficient first. Well, we're going to use a relation table between Reynolds number and drag coefficient. While using this information, we find out that the drag coefficient of wire is equal to 1. And then we put all the information in the ratio drag wire per the drag wings. And as you can see, we cancel out some variable. And finally, we got the ratio equals to 0.225. So that is how it works. Let's move to the next one. Last but not least, it is chapter 15, compressible flow. This is probably the hardest chapter to learn since it will recall all those thermodynamics nightmares. Basically, it covers, of course, ideal gas thermodynamics, stagnation properties, Mach number, and flow regimes in compressible fluid. To practice this, we are going to solve exercise related to stagnation properties. As you can see, at number 13, we're gonna have a pitot device and thermocouple connected to a flow stream in a tube. So what we are going to do, we need to find the air velocity and air mass flow rate. So how we do it? Let's move to the solution part. The first one, we need to point out that it is not a incompressible flow. This is a compressible flow, so we need we need to use a different equation. Let's say we assume this is an isentropic flow, and to find out the velocity, we're gonna need the Mach number. And let's find out the Mach number first. Okay, let's zoom out, zoom in. We're gonna use the ratio of pressure like this of isentropic flow, and there are also another parameter key. It is the Rayleigh flow, which equal to 1.4. We put all these parameter back, and finally we got the Mach numbers equal to 0.8929. We're gonna use this Mach number to find out the velocity, which equals to Mach times coefficient C. This coefficient C is equal to roots of a Rayleigh flow, Rayleigh coefficients, and then ideal gas constant and temperature. Ideal gas constant will be derived from this table, as you can see. Oops. Yeah, for air standard, we get gas constant equals to 1.716 to the power of 3. And we're gonna put down all those parameters. And finally, we find out the velocity is 979 feet per second. We use this number to find out the air mass flow rate, which is equal to 2.42 slug per second. Okay, friends, I think that's it. All the review and exercise of my study at the half semester in my class. I hope you really enjoy the discussion and it really helps you understand more about fluids mechanics. So yeah, thank you for your attention and bye bye.